Go
Good
ahead.
morning, good afternoon, good evening, whatever the time zone you are. So today I'm going to talk about some new features that have landed on user-defined functions for HDF5 that bring computation even closer to the data, and I do hope you enjoy it. So let me begin by recapping what HDF5-UDF is and how it changes the way that people interact with datasets. As you are aware, a traditional application has a write path in which a piece of data is provided to the write function. And in its simplest form, data is just written contiguously to disk and retrieved back when the application wants to read the data set. And it is also possible to compress the data by chunking and delegating each chunk to a compression filter. And then when it's time to read the data back, the decompression callback executes and provides the original data to the calling application. User-defined functions, on the other hand, they introduce a new way to retrieve values of a data set. So instead of storing and reading static data, we let applications to provide a piece of code that contains instructions on how to dynamically generate values for a data set. Such instructions are then compiled from the perspective of an HDF5-aware application. Such datasets look just the same as a regular dataset in the sense that they are named, they have types, they have dimensions, and they can be accessed using the traditional APIs. But underneath, reading them is different because the read operation is actually bringing the compiled object from the file. And then our engine invokes the UDF handler component, which executes that compiled code and populates the output dataset on the fly. And the technology that is enabling this to come to life is precisely the same one that enables filters to exist, which is the I/O filter interface. Also, we have a few examples here on what a UDF dataset looks like. Here we have an example of how a declaration of a UDF dataset looks for the Python backend. In this case, we have a dataset named C, which is being composed by the sum of datasets A and B. And you see that we have a lib namespace, which provides functions to access both the input and the output datasets. Those functions written in Python are compiled into bytecode form. And then at runtime, we invoke the CPython VM to interpret that bytecode. Also, note that we do not have a return value from this function. And that's because we exchange data using foreign function interfaces. So no data copies are needed. We are accessing the final buffer when we write to C. C++ looks just the same, but we are then compiling the code using GCC RClang. And Lua is also supported, in which case we rely on Lua JIT, which leverages a just-in-time compiler to speed up the execution of the UDF. Also, there's one last piece of information in that the stack we have enables the execution of UDFs in a sandbox. So any attempt to execute a system call or to access a path that has not been explicitly allowed results in the termination of the UDF process. And by default, UDFs that have been signed by an unknown key have a restricted access to system resources. Basically, we do not allow any access to directories or to execute any system call at all. On the other hand, we have system calls that, UDFs that have been signed by the current user and that are executing on that same system. So it makes sense to just let those processes to run as if they were a regular process. So in that case, we do not impose any restriction whatsoever. And we have a mixed mode in which users can customize the access rules for known keys, so they can, for example, allow UDFs to import certain programming language modules, for instance. Now, given that we have this architecture that enables people to create dataset values on the fly, we decided to think about what's next in terms of architecture and interesting things we can do with this platform. So I have decided to create a new extension to integrate HDF5-UDF with the new stack from NVIDIA called GPU Direct Storage, or GDS for short. And this stack basically allows one to transfer data from storage, say NVMe, to the GPU without having to rely on the CPU. So basically, you do a direct transfer of data using DMA. So this new backend, it is able to process source code written in CUDA. So here you have a dynamic dataset entry point. So we are basically computing the same code as I have shown before. But here, the actual code that computes the NDVI value in this example, it is a kernel that executes in the GPU, right? So we take this piece of code, we generate a shared library that is saved to disk, and then when the user loads this data set, we invoke the UDF handler that DL opens that library and then executes it. Also, any dependencies that this UDF has, such as the variables read and NIR, they are directly transferred from the HDF5 file using DMA to the GPU memory. And this implementation also supports decoding chunks compressed by the Snappy algorithm. So instead of just supporting contiguous data sets, which are kind of simple to support, right? You just read the data and it's ready to be consumed. This implementation supports decompression of chunks compressed by Snappy, in which case we transfer them straight to GPU memory. And then we upload a decompression kernel that is able to decompress chunks in the GPU and outputting the decoded data straight into the output data set. And then once we have that data prepared, we can finally execute the UDF kernel that we have compiled and loaded from disk before. So as you can see, there's a lot of things going on under the hoods, yet the UDF remains simple, right? It's very similar to the UDF that I have shown before, written in Python, in C++, or in Lua. So HDF5-UDF provides all required abstractions to transfer data back and forth between the storage device, the GPU, and the calling application. And now I'd like to show you some numbers that I have collected and I'd like to share with you. On the left-hand side of this figure, we have the time it takes to execute the UDF that I shown before. So UDF that it's basically a UDF that takes input from 2 chunked data sets and that computes the NDVI, which was that simple mathematical expression here. So it's just a division, basically. The dashed line that you see in light blue color here is indicating the time it takes to read 1 chunked data set from NVMe. It could be the read or the NIR data set. The contiguous lines that we see below this dashed line are the time it takes to execute the UDF. That is, it includes the time to load the 2 data sets from NVMe, to transfer those 2 data sets to GPU, to decompress them on the GPU, to execute the UDF, and to transfer the data to the application. And that's faster than reading 1 chunked data set using the H5 API alone. So this is really cool. This is exactly what I was expecting to see when I started this implementation. So I was quite happy to see that GDS is something that can benefit quite a lot this kind of application. We can also see that at the very top of this curve, we have a dashed line showing the performance of the CPython VM, and it's quite slow in comparison to the other backends. So we see that it is costly to execute Python code. It's not so dramatic, but it's costly. So for those who are seeking performance when writing UDFs in Python, it may be worth to consider using a different Python implementation, such as PyPy, for instance. Now, on the right-hand side of the figure, we see the time that it takes to execute the same UDF as before, but in this case, the dependencies are stored as contiguous data sets. They are a contiguous layout, that is. So in this case, there is no need to decompress data. So in the simplest case, we just have the retrieval of data from the application, and it's quite quick to do so. when we execute this version of the UDF that's compiled for CUDA, we do have some overhead because we basically have to transfer the data and then we have to copy the data back to the user buffer. So there is some overhead involved here. So unless we have some large data set sizes, we are not going to see any benefits of using GPUs in this case. Now, there's a catch here. It was only after I have prepared this material that I noticed that the GPU card I had belongs to the family of cards supported by GDS. However, all data transfers were not conducted via DMA. They were actually happening via software initiated copies. So it looks like we should get even better numbers if we were to use DMA transfers, which I was kind of saddened because this is not the final numbers I was expecting to see, but I'm also happy because we're going to get even better than what is being shown here. So it looks like I'll have to chase some system that's GDS ready so I can capture the final numbers. If you happen to have such a system and are happy to help me to run those experiments, please do let me know. So do I still have time?
Yeah, you have about a couple more minutes, yeah.
Okay. So now I would like... Okay, so let me show you now something just to keep the tradition. Let me share a different screen this time. Okay, I hope you can see this. Do you see my terminal?
Yes.
Okay. So I'm going to show you now something that's unique that only a user-defined function can do. What I have here is a special UDF. And what it does is it's going to boot Linux. So this is the HDF5 file I have. It contains binary blob, which is a data set that's only binary data, that I'm calling kernel. This is basically a kernel that I have compiled for x86-64. I also have an initial RAM FS image that contains a small file system that is basically able to boot a Linux system and print a message. And then I have a UDF data set that I'm calling console. And what this UDF does is it reads the init RAM FS and the kernel datasets, saves them to disk, and then it invokes QEMU, the QEMU hypervisor, while outputting the output messages from QEMU to a telnet-based interface. Then I connect to that interface, to that TCP port, and then I basically read the lines that are being output by that process. And as you can see, here I'm going to dump the contents of this data set. And yeah, voila, here you have it. We have booted Linux on the fly. This is the contents of the data set. You can see it's here is the kernel buffer messages being printed out. And finally, we have welcome to HDF5-UDF Linux. So yeah, this is it. This is something that it may look like something that not everybody is gonna want to use, but it could be used to, for instance, create UDFs that have a lot of dependencies that are complicated to ship or to install on a given system. You could use something like this to embed all the dependencies you have and quite easily reproduce or create data sets with dynamic values on the fly anytime you want. So with this, I conclude my presentation. I am happy to take any questions that you might have now. And thank you so much. I hope you have enjoyed.
Yeah, thank you so much, Lucas. It's always exciting to see your presentations.
Thank you.
We have a minute or two to take questions.
Hey, I have a question. This is John.
Hi, John.
So you mentioned like the system dependencies. So how does that work? If like move a file somewhere else and then the UDF executes, if those system dependencies aren't there, it sounds like there'd be trouble.
Yes, there will. Yes, it is basically a piece of code that you're executing. So if it's attempting to load a data that's not there, you're going to have a file error.
I mean, not just the data, but like, let's say your code requires some library that's not on.
Right. Yes. You're going to have a problem because the dependencies will not be fulfilled. We do have plans to incorporate support for the declaration of dependencies. So we could, for instance, run pip install on the fly. But that is not something I have started yet. It's just a plan. I still have to draft the system so it can support all the languages we have today.
Yeah, when I was working with AWS Lambda, what they do is you provide like a Docker image, right? So the image can be set up however you want, and then that's the context in which the function executes. Unless that's practical for your UDFs or not.
Yes, I have also considered creating support for containers. I have even talked to Gerd about this, but in the end, it was just quicker to come up with this VM approach. It's everything is there already. But yeah, it's something that we could do if there is demand for that. It's not a big deal to provide that.
Cool.
Okay, cool. Thank you. And, yeah, Lucas just wanted to mention that CJ Newburn from NVIDIA would be excited to see this work on GDS. So I can make you the connection if needed. And he may, depending on how it works out, he may provide you access to GDS systems. And I also have a system with GDS. If maybe we can connect.
Hey, all right. Sounds like a good plan. Thank you so much.